Well, I'd like to thank everybody for being on to our second webinar on rethinking phosphorus management. We definitely want to thank the Illinois Soybean Association, the Illinois Soybean Checkoff, the Illinois Fertilizer and Chemical Association, and the Illinois CCA group for sponsoring and partnering on these series of webinars. My name is Pete Fondel. I'm an associate professor at Illinois Central College in the Agriculture Department, and basically emceeing this event. What I'd like to do real quickly is introduce our speaker, Dr. Tom Bruulsema, who's a phosphorus program director for the Illinois Plant Nutrition Institute out of Ontario, Canada. And Dr. Bruulsema has basically led research and education programs for the Eastern Institute of Eastern Canada and Northeastern United States since 1995. He's been recognized as a fellow of the American Society of Agronomy, the Illinois Soybean Society of America, and the Canadian Society of Agronomy. He's also played a key role in the 4R nutrient stewardship and basically co-edited the IPNI 4R plant nutrition manual that most of us are probably familiar with. If you have questions during the webinar, you can type them into your computer and we'll be answering them, or I'll be reading them at the end of the presentation, and we'll see if we'll answer those towards the end of the program. So with that, I'll turn it over to Dr. Bruulsema for his presentation.
Thank you kindly, Peter, for that introduction. As Peter mentioned, I'm Tom Bruulsema with the International Plant Nutrition Institute, and honored, in fact, to be asked to be the second speaker in this series on rethinking phosphorus management. What I'd like to focus on today, in terms of where we need some rethinking, I want to talk about how the concept of sustainability and managing for sustainability makes it necessary for us to think differently about managing phosphate. And as you can see in my title, Sustainable Thinking 4R Phosphorus, it's going to involve those 4 R's of rate, source, time, and place. And I believe those can make some pretty big contributions to 2 goals that society is expecting of agriculture. Those 2 goals include improving the efficiency by which we use our nutrients, and the second goal is reducing the environmental impact as we continue to remain productive. The organization I work for is called the International Plant Nutrition Institute, and it's supported by primary producers of fertilizer nutrients. We have around 20 member companies, and they're located around the world. My colleagues in the Institute work at places around the world as well, and we try to develop consistent principles for management, responsible use of plant nutrition, and basically we do so by providing scientific information. My outline today: last week Laura Christensen noted that phosphorus is different from nitrogen, that very small amounts of phosphorus can cause water quality problems, and that lots of good phosphorus loss reduction practices are available, but they're not all effective for every location. And she noted that the best option is to keep phosphorus in the field. And today my focus will be on practices in the field. In particular, it's the 4 R's of nutrient stewardship. The right source of phosphorus at the right rate, the right time, and in the right place. I'll explain how this 4R program connects to sustainability and its key issues, crop yields, soil fertility and health, natural resources consumption, and water quality. And then I'll discuss how several recent initiatives have implemented 4R principles, and these initiatives include the Western Lake Erie 4R certification, centered in Ohio, and 2 new specialties that are recently introduced to the Certified Crop Advisor program. The slides I'm showing you today are available in PDF at the website indicated here, phosphorus.ipni.net. Intense rainfall on conventional tillage moves soil, and that's, in our traditional thinking, been the big thing in managing phosphorus loss. When we're managing the total phosphorus loss from soil, that is the big mover. This example of erosion resulting from a sudden 2.5-inch downpour within 1 hour came from a few years ago from my brother's farm, the farm where I grew up, south of Hamilton, Ontario. While the farm has transitioned from annual moldboard plowing to rotational chiseling before corn, you can see that keeping erosion under control is still important, but it's still an issue as well. When we go to some of today's conservation or no-till practices, we control a lot of soil erosion. This situation here showing snowmelt runoff has certainly got erosion under control. But nevertheless, the water that's running out almost clear could be high in the invisible dissolved form of phosphorus under certain conditions. There are a few critical manageable factors here that could influence the dissolved concentration in that water. If the surface of that soil is unreasonably enriched in phosphorus, if that soil has been receiving inputs in excess of crop removal for a long time, that water could still be enriched. If there have been recent applications of fertilizers or manures on the surface of that soil as well, that water could be enriched. But if the soil is managed under reasonable conditions and soil stratification is also kept under control, then you can expect that the concentrations will be fairly reasonable as well. Runoff does happen. We needed to manage phosphorus to minimize its exposure to runoff. In the 4R nutrient stewardship concept, right means sustainable. We look at 4R as a means of building public trust to ensure the sustainable future of our industry. The food supply chain wants to improve the environmental footprint of its products, and for this reason, we're engaging with Field to Market to represent 4R practices for managing both nitrogen and phosphorus in its field print calculator. Applying 4R principles ensures consistency of messages and actions all along the food industry supply chain. The 4Rs include adaptive management. Our vision of adaptive management for plant nutrition includes cycles of decision, action, and evaluating the outcome. We get consistency for all scales by making sure that the evaluation criteria, essentially the performance metrics, are the same for all. What's new in sustainability thinking is that profitability is no longer the only performance metric. It's still an important one, of course, because no unprofitable farm can be sustainable. But our rethinking for phosphorus management is profitability and soil health, profitability and soil phosphorus fertility, profitability and water quality. How do we fit these metrics into the bigger picture? The crop nutrition industry has been talking internally about performance metrics for quite some time. We, the Fertilizer Institute, IPNI, Fertilizer Canada, got together and classified these metrics into enablers, actions, and outcomes. I want to focus today on the actions and outcomes. From the sustainability perspective as an industry, agriculture needs to better document its actions and link them to outcomes. From the phosphorus perspective, the actions are the source, rate, time, place combinations in which phosphorus is applied, and the key metrics are productivity, soil health, nutrient use efficiency, and water quality. Those remaining in the list of 9 are also important, but they're highly related to the first 4, and the first 4 interrelate among themselves quite well in addition. 4 R's of phosphorus application affect them all, and these are the 4 impact areas that I'll be dealing with in the rest of this webinar. When we look at the impact of a nutrient like phosphorus on productivity, it's important to understand how much of it the crop takes up, when it's taken up, how much ends up in the grain. This and the next few slides are compliments of Dr. Fred Below at the University of Illinois. These 2010 data from 2 sites and 6 hybrids show that high-yielding corn can take up as much as 100 pounds of P2O5, and that the uptake continues to the day of maturity for the corn crop, and that almost 80% of it ends up in the grain. No other nutrient is as efficiently mobilized into the grain as phosphorus. Since it's also removed with harvest, it has always been important to base rates recommended on replenishing this removal, usually by accurately measuring the yield goal and applying a coefficient. For corn is generally around 0.35 pounds P2O5 per bushel, and that's precisely what it turns out to be in this example. Dr. Bielow's research has been exploring whether the high yields aimed for with intensive management, high populations, narrow rows, and high levels of other inputs require higher levels of soil phosphorus as well. Part of his research program examines right place. This machine applied phosphate fertilizer in a band 4 to 6 inches deep under the future crop row, and their treatments were comprised then of placements that were either directly under or at various distances from that row to examine what the effect would be on the growth and physiology of uptake of the plant. Visual observations suggest that the corn seedling growth responded to the nutrients placed in that band, noting that those nutrients included things other than phosphate as well, including nitrogen, sulfur, and zinc. Comparing an untreated control to those that had bands either 6 inches away from the row or directly below showed that the seedling response was strongest when the nutrients were directly below. It's also important here to compare the form of placement. Where the nutrients are broadcast, we're not getting quite as high a yield as where the nutrients are banded directly under that row. And you can see from the untreated control that this was definitely a site that responded to phosphate fertilizer with at least fairly high yields. Not all seedling responses translate into yield, but these data showing the final yield attained over a series of distances between the deep band and the row confirm that at short distances, band placement supports higher yields than broadcast phosphorus, and both produced higher yields than the untreated control. These data support the need for phosphorus and the agronomic efficacy of band placement. They may suggest, but they don't really confirm, the need for higher soil test phosphorus levels as crop yields increase. It may still be sufficient to just replenish the higher nutrient levels removed at the same optimum level of fertility. Dr. Bielo points out that the individual plant's root system is most dense within a 6-inch radius of the base of the stem. For this reason, and also considering the importance of early season crop nutrition for phosphorus, band placement is effective agronomically. We are often asked the question, how much does fertilizer contribute to yield? It's not a simple question to answer. It depends on the time frame under consideration and the initial fertility levels of the soil, as well as many other factors. In general, many sources of information attribute at least 40 to 60% of crop yield to the use of fertilizer. In this example, a 40-year study on irrigated corn in Kansas, yields are 60% lower without nitrogen and phosphorus combined, 27% lower if only phosphorus is missing. So we could say that long-term, at least a quarter of our crop production depends on the phosphorus we are applying and wouldn't be there without it. I have to apologize. It looks like on this slide I have a graphic missing. The graphic is taken right out of the Illinois Agronomy Handbook and shows the response curves as a function of soil test phosphorus for soybean, corn, and wheat. So you'll just have to imagine that it's there. The short-term yield effect of phosphorus is quite a bit different than the long-term. And in fact, many of our soils built up to optimum fertility levels, we really do not expect a crop response in the year of application. But there are a number of soils that are below critical levels, and in those situations, we expect on average a response of about 15% for soybean. We'd lose about 20% of our yield for corn and about 40% of our yield for wheat if we were growing those crops on those soils with no phosphorus fertilizer added. So even though the short-term response is small, phosphorus use in agriculture clearly plays a large role in supporting increased productivity, the first of our 4 key outcome metrics. Now I want to look a little bit at the soil test distributions that we see in the state of Illinois and other places as well. So how large a proportion of Illinois soils might be in this responsive zone below the critical level? Illinois actually has 3 regions with different critical levels for phosphorus. 20 part per million is an average. Based on that estimate, IPNI's latest soil test summary estimates that 39% of the soils are below critical. Just as in the 2010 data shown by Laura Christensen last week. Only about 20% of the soils are in the optimal zone where application rates to replenish removal are usually recommended. And that leaves about 40% of the soils testing at levels where either no phosphorus fertilizer is required or at most a small amount of starter supplying less than crop removal would suffice. The wide range of soil test phosphorus levels underscores the importance of soil sampling. The numbers of soil samples taken are generally increasing over time, particularly owing to the increasing use of variable rate application. But if everyone was following recommendations, the proportion of soils in that optimum range should be much higher than 20%. Normal recommendations call for soils below that level to be built up, soils above that level to be drawn down. But we're seeing, even though after many, many years, decades of these recommendations being in place, only 20% of soils being at the optimal level. That does show we have a challenge in managing soil phosphorus better. If we extend to a bit of a wider area by including Indiana and Iowa, the trend over time of increasing soils below critical is less pronounced, but it's still there. You can see by the height of these yellow bars representing 2015 compared to the blue bars representing 2001 that soils in some of the lower categories, we're getting increasing frequencies of those while we're getting reduced frequencies of those that are more in the optimal zone. When we pool all the results across the United States, the full data set, on average soil test phosphorus has changed very little from 2001 to 2015. Nevertheless, again, the range of soil test phosphorus is very wide and thus the soil test is very useful. When we look at individual states like Illinois, we can see that changes of concern when we look at that soil fertility metric. And soil fertility, of course, is an important component of soil health because it feeds the plants and the plants feed the rest of the life in the soil. That's why it is the second of our 4 key impact metrics. The third of our 4 key metrics is nutrient use efficiency. In the case of phosphorus, the most useful expression is the ratio of removal to use. Crop removal divided by the amount applied as fertilizer and manure. IPNI tracks this ratio using a tool called NuGIS, which is publicly accessible on the web. The first point that jumps out of this map is the variability. Unlike corn and soybeans, other crops may need to be fertilized at levels much higher than their nutrient removal. And then there are areas with high soil test phosphorus that can produce high yields for many years while being fertilized with less than they remove. But look at just how widely these ratios vary. A large section along the southern Mississippi River, colored in red, where 5 times more phosphorus is being removed than is being applied. And then if we move to the east, we see pockets of agriculture where the amount being applied is 5 times the amount being removed. Some of these areas have opportunities for improved efficiencies. The phosphorus balance also varies over time. Here I plot the sum over all of the USA of phosphorus applied as manure in red, as fertilizer in blue, and the sum of the two as the green line. And compare that then to the purple line, which represents crop removal. We can see that on average over the country as a whole, phosphorus most often is applied in a slight surplus. We need to keep in mind though that where manure is applied, it's often applied considerably in surplus of crop removal, and thus therefore there's probably large areas as well where applications are not replenishing all that the crops remove. And a case in point here is the phosphorus balance for the 3 states combined, Indiana, Illinois, and Iowa. For the most part of the past 20 years, on average, they've been in deficit, except during 2012 when drought dramatically cut crop removal. So the nutrient use efficiency metric, in this case the phosphorus balance, is providing us insight into why soil tests are changing, and it's helpful in predicting future impacts of current phosphorus management practices on productivity. The phosphorus balance is also quite scalable. It can be calculated quite easily at farm level, regional levels, or national scale. What we don't include in NUGIS is biosolids, and they too can be a useful but small source of phosphorus. The amount of phosphorus in biosolids is roughly equal to the dietary phosphorus supply, and it's really equivalent to about 8% of total crop removal in North America. And only about half those biosolids are currently being land applied. They're applied to less than 1% of the cropland. They can be a useful source of zinc and some of the other micronutrients as well. And over the past decades, a lot of improvements have been made in terms of managing the metals issue and several other issues with biosolids. And there are a number of processes have been developed to make the materials more useful agriculturally. They still have a lot of issue with bulk and transportability. And another thing to keep in mind is that the concept of a guaranteed minimum analysis that works well with commercial fertilizers does not always accurately represent the total nutrient value in a biosolid material. Now, all of these considerations, this phosphorus use efficiency, is a sustainability concern because a lot of the public looks at our industry and says, you're a mining industry, you're extracting from finite natural resources. And if you're using it inefficiently, then it's a concern for future generations. So a lot of concern has been raised over many decades about how long will the phosphate rock reserves last. We do want to minimize depletion of a finite natural resource, and there's been a recent surge since 2009 with the emergence of the peak phosphorus concept, a surge in discussions about how long the current reserves will last. Estimates of the end of phosphate reserves range from decades to centuries, but most authorities are now accepting that it's at least 100 years away. The 2010 report of the International Fertilizer Development Center resulted in almost a 4-fold increase in the estimate of world total reserves. Previously estimated at 16 billion metric tons, they are now considered to be about 69 billion metric tons. A lot of that increase was for the country of Morocco, a country that still has vast resources in addition to those reserves. A simple calculation of reserve life, dividing current production levels by reserves, gives an estimate of about 314-year phosphate rock supply for the world. We've seen, however, that global phosphate consumption is increasing and it's forecast to continue increasing, and that would result in this estimate being an underestimate. But we've also seen over time that new resources get added to reserves and that the reserves are not a static number. In that sense, these estimates of reserve life are conservative. With recent revisions to the estimates of reserves, the estimated life of phosphorus reserves is now similar to those of potash and magnesium, well into the hundreds of years. It's worth noting that the estimated reserve life of the important micronutrient zinc is far shorter. While we agree that phosphate rock is a finite resource and should be used carefully, this sourcing issue seems to many of us less urgent than the final fate issue, the impact of phosphorus losses on water quality, which is the fourth of our key impact metrics. One example of a water quality issue related to phosphorus is Lake Erie. As the shallowest and warmest of the Great Lakes, it's particularly prone to algal blooms. Its watershed is the largest and most heavily influenced by agriculture. This watershed is also located on the eastern side of the Corn Belt. Generally, it gets more rain and its soils hold less organic matter as compared to Illinois and Iowa and further west. These factors may influence the forms and seasonality of phosphorus loss impacts. In other words, some practices like broadcast application and late fall application may have different risks here than where you work. Algal blooms in Lake Erie have increased since the mid-1990s, just over the past 20 years, along with monitored increases in dissolved phosphorus in its tributaries. The largest tributary, the Maumee River, drains around 4 million acres of corn and soybean cropland. The phosphorus loading during the March through July period in the dissolved form, represented as DRP in these figures, has been increasing on, and in 2015, owing to very high rainfall in June and July and very high river flows, both the concentrations and total loadings basically set records. Under the Great Lakes Water Quality Agreement, reduction targets of 40% have recently been set using 2008 as a baseline. A 40% reduction target is quite ambitious. This is a level of dissolved phosphorus in terms of flow-weighted mean concentration that hasn't been seen in the Maumee River since 1999. And the aim of this program is to achieve that condition 9 years in 10 by the year 2025. While some nutrient loss impacts show correlation with nutrient use efficiency, the increasing trend in dissolved phosphorus is not linked to increase in phosphorus surplus. In fact, if we look at the same kind of NUGIS data representing fertilizer and manure applied relative to crop removal in the Lake Erie watershed, what we see is that crop removal is increasing over time, but relative to the nutrients applied, relative to the phosphate applied per acre of land there, you're not seeing those increase, and in fact the last few years have seen deficits of phosphorus more frequently than they've seen surpluses. Crops are removing more phosphorus, but application rates have generally not increased, and so we really can't say that this is a rate issue. But at the same time, we can see that fertilizer comprises a large amount of the phosphorus input for this watershed. And so we need to be asking ourselves, is there something about source, timing, or placement that's manageable? There are many theories as to why dissolved phosphorus losses are increasing. Some attribute it to no-till, some to the fact that very little true no-till is actually practiced. Some attribute it to less acidity in the rain. Not all the contributing factors are known, but there are some obvious combinations of source, timing, and placement that could help reduce risk of loss. So over the past 5 years or so, a 4R certification program for ag retailers has emerged for the Western Lake Erie Basin. The program involves many criteria related to training, record keeping, recommendations, and custom applications. Here are some examples of the program criteria. 4R recommendations include all sources applied so that the phosphorus value of manure and biosolids is not neglected. Under the right rate, typical land-grant university recommendations are required unless results of adaptive management research in the local area support something different. Under right time, application on frozen or snow-covered ground is ruled out, and there is a criterion requiring the applicator to watch the weather forecast for storm events that could generate runoff. The criteria encourage right place application using variable rate, injections, subsurface banding, or incorporation wherever possible. As of a few months ago, the program has recognized 25 branch locations with third-party verified certification. These 25 locations reach a total of 1.8 million acres, 1.2 million of which fall in the Lake Erie watershed. Some important principles apply to the understanding of how dissolved phosphorus can be lost. First, it's important to understand that fertilizer phosphorus is soluble. So is a large part of the phosphorus in manure. We have always taught that phosphorus doesn't move much in the soil, but that assumes it gets a chance to interact with the soil. If the first rain that meets a granule of phosphorus on the soil generates runoff, that runoff will be enriched in phosphorus, and it takes only a very small amount to exceed the limits for controlling algal blooms. Here is one case documenting how surface application of phosphorus without incorporation can increase loss of dissolved phosphorus in tile drain water. This field had a history of no-till. And in fact, these are two separate fields with the same tillage history. It's located in the center of Ohio, actually just a little south of the Lake Erie watershed, but on a soil that's very similar. It's tile drained silt loam with the soil test at an optimum level, 30 parts per million by Melick 3. Fertilizer is applied on the 6th of May. 2 days later, one field was tilled with a disc and the other was not. In these fields, the main pathway of water flow was through the tile drains. And using this as a before-after control impact design experiment, we were able to make some comparisons. This work comes from Kevin King and Mark Williams with the ARS in Columbus. So before phosphorus application and before tillage, the flow represented in blue, and the phosphorus concentrations and the phosphorus total amount basically was the same for the two fields, TD1 and TD2. On the 12th of May, there was a rainfall event that caused the tiles to start flowing. And you can see that the incorporation of the phosphorus with a disc modified both the water flow and the phosphorus concentrations. So obviously the disc is closing some of the macropores that allow a lot of the water to get to the tile. So the total flow was reduced, but also the phosphorus concentration of that flow was reduced. If you compare the field where the phosphorus was not incorporated to the field where the phosphorus was incorporated, by working the phosphorus into the soil, macropore paths were disrupted, less water was lost, and both concentrations and loads of phosphorus were reduced about 5-fold for the first event and by 70% over the first 5 events that occurred after fertilizer application. The total loss was only 0.8 of a pound, but you can see the concentrations reached nearly 5 milligrams per liter, exceed by about 100-fold the target for the Maumee River. Conservation tillage has been credited with reducing erosion and improving soil health. And these benefits could be negated by a requirement to incorporate fertilizer with a disc, but we can also ask ourselves, could an alternative placement, even in traditional starter bands, have been just as effective? Do these results apply to soils in all landscapes and of all textures? It is not the only piece of evidence, however, that indicates high loss potential of soluble phosphorus associated with leaving fertilizer or manure on the soil surface. Here's another study that whose results also confirm that small amounts of phosphorus loss can dramatically increase concentrations in runoff. And this particular study was done with artificial rainfall in a no-till field near Waterloo, Indiana, in the Maumee River watershed. Part of the field was tilled with a finisher chisel plow in the spring. Then a rainfall simulator was brought in for the second half of June. One day after applying phosphate fertilizer to the soil, rainfall was applied at 2, 3, then 1, and then 4 inches per hour. The resulting runoff had high phosphorus concentration. You're talking 10 to almost 20 milligrams per liter, or parts per million. It's many times higher than the target for the Maumee River. Losses from either soil amounted to less than 10% of that 100 pounds of fertilizer that was applied. The tilled soil lost less than the soil that remained no-till. Losses prior to fertilizer application, however, were many times lower than what is shown here. So the main point is that leaving the phosphate fertilizer on the soil surface is the big risk. The second point is that the risk of leaving it on the surface is particularly high in no-till. One important interaction between tillage and phosphorus application needs to be considered. With less tillage, there is more stratification of the soil test. These long-term data from Indiana show that the top 2 inches in no-till increased to as much as 3 times the level of the top 6 inches. The top is what interacts with broadcast phosphates and with surface runoff and with the water running down macropores. In soils susceptible to either form of loss, stratification needs to be managed. Higher soil test phosphorus means less soil capacity to hold on to freshly applied phosphorus. And the high soil test P in itself is a chronic contributor. Every runoff event is enriched, not by a lot, but higher than with a normal optimum level of soil test phosphorus. These data from an Oklahoma wheat study show that the typical effects of tillage on the 2 forms of phosphorus loss. The results are a summary over several watersheds. Going to no-till reduced total phosphorus concentrations in surface water from around 5 parts per million to less than 1, but it increased the concentration of dissolved phosphorus about 4-fold to almost all of the 1 part per million of the total being lost. Many studies show similar results. It should be noted that the fertilizer placement here was on the surface, and the no-till implementation also reduced grain yields. In situations where fertilizer is banded subsurface, you might expect less increase in the dissolved phosphorus runoff. So far, we've been reviewing edge of field losses resulting from specific events. Studies by Heidelberg University offer an opportunity to assess loss at the watershed level as well. The Honey Creek watershed drains about 95,000 acres, most of which are cropped to corn and soybeans with a little bit of wheat. In the fall of 2011, rains were limiting access to the fields and time was tight for harvesting and fall fertilizer application. Finally, in mid-November, there came a gap large enough to dry the soils and allow field activities. All the time, water flow and its dissolved phosphorus load were being monitored. The water flow in the blue, dissolved phosphorus concentrations, the black dots. Generally, phosphorus concentration increases with water flow, but following periods where fertilizer applications had been made, concentrations relative to the flow increased sharply. This finding led Heidelberg University researchers to conclude that though the loss per unit area was quite low, fall applications just prior to runoff generating rain was a risk factor, sending stream concentrations far above target levels. Again, here we're seeing a stream, the Honey Creek, getting up to almost 1 part per million in phosphorus, relative to the target concentration again for the Maumee River would be something like 0.05. The total loss, hardly 1/3 of a pound of P2O5 per acre in this one single event. And you can see that the losses diminish as you get further away from the actual fertilizer application. Currently, about 4% of the phosphate fertilizer in the Lake Erie watershed is applied in strip-till bands, an innovative method for putting phosphorus in the right place while keeping crop residue in its right place. The system requires RTK GPS for precision planting, and it takes more time than fall broadcasting. But it raises some questions as well. How will we motivate expanded use of this system? If we put a cover crop in this system, how much more productive can we make it? And can this system increase yield potential as suggested by Dr. Belo's research in Illinois? Here's another approach with the ETS Soil Warrior. This machine can move faster because the strip tillage is done with discs. The phosphorus is mixed with the soil, but not as deep as when knifed in, or as in Dr. Belo's research. One dealer in southwestern Ontario is evaluating this system. There are some growers, this is from a field trip I had last summer, where he's growing 3 crops, corn, wheat, and soybeans. Every crop receives its phosphate fertilizer, either in a band near the seed or in a band with the seed. Equipment does exist by which we can place phosphorus in the soil and avoid the need to be broadcasting it on the soil. The choice of practices in an adaptive management approach needs to consider all the advantages and limitations of the different source, rate, time, place combinations that are available. Essentially, these are the costs and benefits in terms of key outcome metrics. These costs and benefits will differ in different regions. The results I have shown from Ohio and Indiana today may or may not apply to Illinois and Iowa and Minnesota, or they may apply, but only to some parts of those regions. The nutrient reduction strategies of Iowa and Illinois so far include consideration only of total phosphorus loss, not dissolved. And I believe it's unknown what role dissolved phosphorus losses are playing in some of those areas. Moving from practices with risk of elevated phosphorus in runoff may entail a lot of cash costs. Broadcast application offers flexibility in timing and often the lowest application cost. In soils with optimum phosphorus levels, band and broadcast application do not differ in terms of availability to the crop and crop response, but they do differ in risk of runoff loss. To minimize phosphorus losses from broadcast applications, it's important to apply them when the risk of runoff is low. Runoff events are more frequent in the late fall, winter, and early spring. Ideally, all phosphorus would be applied at planting, but limited storage capacity and equipment availability often make this impractical. Practices like fall band application with strip tillage or zone tillage or point injection need to be considered. We need more research to accurately quantify the benefits and costs of these practices to help in making these decisions. So essentially, this list of benefits and costs, if you could put it into a context of a sustainability system, what you're looking at is ideally the economic, the environmental, and the social. And each of them may have costs or may have benefits. And then this is essentially, if we can compare our source, rate, timing, and placement on a triple bottom line rather than just an economic one alone, then we have a true sustainability system. The certified crop advisors are crucial to the implementation of 4R nutrient stewardship. The 4R nutrient management planning specialist will be expected to have a higher level of knowledge about managing environmental risks associated with nitrogen and with phosphorus. This program's been implemented last year, and a good number of people have already taken that exam in the last 2 sittings. There is a version in development in Ontario as well that is specific to the needs of the Canadian context. The sustainability specialist will have broader knowledge about how to connect to sustainability systems and report on key performance metrics. And this set of performance objectives have been in place since almost a year ago. The specialty was launched in November in Minneapolis. The first exam is scheduled to be held this coming August, And I should note that this sustainability specialty exam references 4R nutrient stewardship for all the aspects that touch on nutrient management. But of course, it covers many other aspects relevant to sustainability as well, including the management of pests and the management of specific crop aspects as well. So in summary, sustainability thinking balances the economic, environmental, and social costs and benefits. Our 4R rights, right source, right time, right place, right rate, need to consider consumer and public priorities in assessing the impacts of management practices. And so when we get to the specific context of managing phosphorus with 4Rs, we need to keep the 4 things in mind, 4 key metrics. Measure how we're keeping phosphorus from limiting crop yields. We need to be measuring how we're maintaining optimum soil phosphorus levels and minimizing stratification. We need to be efficiently using finite natural resources, ensuring that where we have manure resources and biosolids, we're making use of them as well. And then we need to be ensuring that we're improving water quality by reducing phosphorus loss just by the right combination of timing and placement. Again, the URL where these slides are available is phosphorus.ipni.net. If there is time available, I am ready for any questions you might be willing to ask.
Yeah, Tom, I do have a couple of them here. One question that was submitted was, could you discuss or give your opinion of the Haney and Solvita test?
I would have to say I'm not fully familiar with the Haney and Solvita. My understanding is that the main aspect of it is a measure of carbon dioxide efflux from a soil sample in incubation, and certainly that's a measure of active and available organic matter, which is indeed what the soil microorganisms thrive upon. At the same time, while that's one aspect of soil health, I don't think it necessarily reflects everything that's necessary for maintaining a healthy soil. A healthy soil has to have the right physical characteristics, the right chemical and biological characteristics. And it's important to be ensuring that we are keeping all those characteristics at levels that support the growth of our crops, because essentially our crops are the primary producers, the primary feeders of energy and organic matter for those soils. So the test can be useful. At the same time, I don't see it replacing the need for traditional soil testing and also measures of soil physical properties. I think that through my presentation here, it's become abundantly clear that the soil's capacity to absorb water is a very important property. If our soils are generating more runoff than they used to, it's part of the phosphorus loss issue. And if we can improve our soil's ability to infiltrate during intense rainstorms and retain water, that's a very important property that influences both productivity and also minimizes environmental impact.
And another question, so based on the data presented, do we know where in the soil profile we are low in phosphorus?
That's an interesting question. In the past, we always took soil samples to 6 or 8 inches deep, assuming that was the plow depth, and it was more or less a well-mixed layer if we were moldboard plowing. In current tillage management systems, where the moldboard plow has become almost rare, fizzle plows don't do as much vertical mixing as the moldboard plow did, and there are many tillage systems that mix even less than a chisel plow. I think you can, in most instances, assume that even when phosphorus is placed into the soil, that we're still getting some stratification happening from the accumulation of crop residues on the soil surface. And that's generally what sampling studies show that conservation tillage is somewhere intermediate between no-till and moldboard plowing. When it comes to stratification, you're going to expect the highest levels of phosphorus near the surface of the soil. When there is the possibility that lower levels of soil test phosphorus a little further down may be limiting in high yield systems. And I think that's what Dr. Fred Belo's research is exploring. We do need to keep in mind that roots are most active near the surface of the soil, where the oxygen levels are better, soil aeration is better as well.
Well, based on this concept of obviously, phosphorus is a tricky issue here, and we have, tillage is causing more erosion, and obviously phosphorus leaving the soil surface via erosion versus going no-till route and having, what you're showing is a higher soluble phosphorus. Where should we all be heading, or what's your opinion of where we should go to kind of address both of those issues simultaneously?
Well, the thing with the webinar is I don't know quite how far everyone listening to me right now is distributed geographically, and I think the important point is to be looking at both. Look at dissolved phosphorus, look at total phosphorus, and find all the information you can on what form is being lost. When it comes to environmental impact, dissolved phosphorus moves further in rivers and has a more direct and immediate impact on algae than the sediment-bound phosphorus. Whereas the sediment-bound phosphorus accumulates in streams and has a longer legacy effect. So both of them are important components, and I think you have to understand both the particular end impact for your watershed, as well as what processes are the ones taking the majority of the phosphorus from your fields to properly answer that question.
Well, there's no more questions that have been submitted at this point. So I guess I'd like to thank Dr. Bruulsema for being on and remind all of our listeners that there'll be another session next Tuesday at noon, which will be Antonio Malario from Iowa State University, talking about fertilizer management practices to reduce the loss of dissolved and sediment-bound phosphorus. So we would appreciate if you enjoyed these presentations, if you'll be on again next week, or if you haven't registered, please do so. And again, we'd like to thank the Illinois Soybean Association, Illinois Checkoff, Illinois Fertilizer and Chemical Association, and the Illinois CCA for their sponsorship and support of these webinars. With that, thank you very much, and hope to see you on next week.